Hello friends, welcome to this video on Jensen's inequality. We will see the statement of Jensen's inequality and when particularly can this be applied or when will this Jensen inequality work and some problems which will involve solving using Jensen's inequality. Come on, let's get started. So before moving on into Jensen's inequality, we need to know about two terms. The first term being integrable random variable. So when is a random variable x said to be integrable? A random variable x is said to be integrable if its expected value, that is e of x, exists meaning it is a finite quantity. So it must not be equal to 0, it has to be something less than infinity. So a random variable x is said to be integrable if the expected value e of x is going to be finite in nature. The second definition which we are going to see is going to be convex function. Twice differentiable, which means f double derivative of x is going to exist. Of a single variable is said to be convex if your double derivative of f of x is going to be greater than or equal to 0 in its domain. So, on given a function f of x, we can say that whether it is convex or not if double derivative of x is going to be greater than or equal to 0. So, what will happen if double derivative of x is going to be less than or equal to 0? Then you call such a function f of x as concave function. Okay, so how will the concave and convex function look like? A convex function will be like this and a concave function will be like this. So look into the word called as cave. So how do we normally draw a cave? This is how normally we draw a cave. So concave function will be like this and convex function will be like this. Geometrically, if we take any 2 points in the graph and we are going to connect them by means of a straight line, if the line is going to be above the curve entirely, then you call the function to be convex. In a similar fashion, if you're going to take any 2 points in the curve and connected by means of a line, and now if the line segment is going to be entirely below the curve, then you call it to be a concave function. So line lies above the curve. Wherever you draw, it is going to be above the curve, and wherever you find it is going to be your curve is going to be above and the line is below, then you call it to be concave. When it is convex, the curve is down, the line is on top. Have this in mind. But practically plotting all the graph and drawing or pointing 2 points and finding a line is not going to work out. So the best way is go for your derivative. Go for your double derivative. If it is going to be greater than 0, it is going to be convex. If it is going to be less than 0, then it is going to be concave. Now, using these two definitions, we now move on to define a Jensen's inequality where x is an integrable random variable. So e of x has to exist for my random variable called as x. And let f be a function from R to R, be a convex function such that f of x is also integrable. Then the Jensen's inequality says that expected value of f of x is greater than or equal to f of e of x. Expected value of the function f of x, which is integrable, is going to be your greater than or equal to f of e of x. So this will be for your convex function. If it is going to be for concave function, then the inequality flips like e of f of x is going to be less than or equal to f of e of x. So this is for your concave function and this is for your convex function. Now Jensen's inequality is mostly for convex function. So you can just try memorizing this formula for application in your problems. Now let us apply these to few problems. Show that the variance of a random variable x is non-negative. We have already seen this property while doing one-dimensional random variable that variance cannot be negative. But how to show it using Jensen's inequality? We will now see that how to define the variance of x. It is nothing but e of x square minus e of x the whole square. So variance of x has to be non-negative greater than 0. So this will tell me E of x square is greater than or equal to, so this is greater than or equal to 0. Take this to the opposite side. So what will happen? This will become E of x the whole square. So in your exams, the problem can also be stated in this way, like show the variance is going to be non-negative, or they can also give you using Jensen's inequality, show that E of x square is greater than or equal to E of x the whole square. Both of them are one and the same. So whatever be the statement, the proof goes in the same way. So to apply Jensen's inequality, the first and foremost rule is that the function f of x, which we are going to take, must be convex in nature. If it is convex, then Jensen's works. Now what is my function f of x? This is going to be x square. F dash of x is going to be 2x, and f double dash of x is going to be 2, which is positive. Therefore my function f of x is going to be convex. And now I know that by Jensen's inequality, by Jensen's inequality, what do we have? We have expected value of your f of x is greater than or equal to f of e of x. So the rule is wherever you have the function x, replace it with e of x. So what happens over here? So this becomes your expected value of what we have taken for your f of x. This is going to be x square, and this will obviously be greater than or equal to function in your x place, replace all your x with your e of x. So in your function, wherever I have x, replace it with e of x. So this will become e of x, and you have a whole square. So this will become whole square. And hence we have proved the required statement. And so you take it to the opposite side. You can also show that variance is always going to be non-negative in nature. So I suppose the application of Jensen's inequality is clear. We will apply to few more problems to see how it works. Now prove that e of 1 by x is greater than or equal to 1 by e of x. So the function of here is going to be 1 by x. I need to first show that it is going to be convex before apply Jensen's inequality. So my f dash of x is going to be minus 1 by x square, and f double dash of x is going to be minus of minus will become plus 1 divided by x cube. So this is going to be greater than or equal to 0, provided x is going to be greater than or equal to 0. Okay, so you have a convex function. So by Jensen's inequality, what do we have? Expected value of f of x is greater than or equal to f of e of x. So expected value of your function f of x is going to be 1 by x is greater than or equal to, in the function wherever I have x, I have to replace it with e of x. In the function wherever I have x, I have to replace it with e of x. Where is my x? Here. So it becomes 1 divided by, replace your x with e of x. So this gives me e of 1 by x is greater than or equal to 1 divided by e of x. By Jensen's inequality, we have proved it. We'll move on to problem number 3. X be a random variable with mean value 10. We have to say what is the value taken by 1 by 1 plus x expectation. So we will try to apply the Jensen's inequality to get the value. By Jensen's inequality, we have e of your f of x to be greater than or equal to f of e of x. So we have e of 1 by 1 plus x. So let me first consider f of x to be 1 divided by 1 plus x. So first I can apply Jensen's only if this is going to be convex. So f dash of x is going to be minus 1 by 1 plus x the whole square, and f double dash of x will be positive 1 divided by 1 plus x the whole cube, which is obviously greater than 0 for your x 1 plus x greater than 0 or x greater than 1. So this is going to be a convex function which works for x greater than, sorry, this is going to be x greater than minus 1, because 1 plus x is going to be greater than 0, x will be greater than 1 taken to the opposite side will be minus 1. So for x greater than minus 1. So now when I apply this, so I will have this to be of the format expected value of f of x, I apply it as 1 plus x is greater than or equal to f of e of x. Wherever I have x, I will have to replace my x by e of x. That is going to be the rule. So 1 divided by 1 plus, so this will become x is replaced with e of x. But there is going to be something given about this e of x, or we have been mentioned that mean value is 10. So this takes the value 1 divided by 1 plus 10. So that makes it as 1 by 11. So the value which my 1 divided by 1 plus x can take will always be greater than or equal to your 1 by 11. So that's how we can say the value taken by e of 1 by 1 plus x. So substitute the mean value which has been given for your e of x, and then we are done. And moving on to the next one, let x be a positive random variable with e of x as 10. Is in Jensen's inequality, find a bound for e of x minus x power 4. So we will try simplifying this expression first. X minus x power 4 is a linear operator, so I can write it as e of x minus e of x power 4. So this will become e of x has been stated as 10, 10 minus e of x power 4. Now I can apply Jensen's for getting the bound. So if this is going to be greater than or equal to something, because e of f of x, but the function over here required is going to be x power 4. So let me take my f of x to be equal to x to the power of 4, and now my f dash of x will be equal to 4x cube, and f double dash of x will be equal to 12x, which is obviously greater than or equal to 0 whenever x is going to be greater than or equal to 12x square. So x square will always remain positive for all the values of x. So this is going to be a convex function. So since it is convex, I can apply Jensen's inequality to it. So by Jensen's inequality, what do we have? Your expected value of f of x is greater than or equal to f of e of x. Now what we have taken for our f of x is going to be x power 4. This is obviously greater than or equal to, in my function wherever I have x, replace it with e of x. So this will become e of x the whole to the power of 4. So this is nothing but 10 to the power of 4. So because we know that e of x is given as 10, so this is 10 power 4. So what is going to be the bound for x minus x power 4? Go and substitute this bound over here. And so my bound for expected value of x minus x power 4 will be greater than or equal to 10 minus 10 power 4. So that solves the problem for this value. And now moving to the last part. Suppose x is greater than 0 is a random variable. Decide which of the two quantities is larger. Whether this is larger or this is larger. Expected value of log of x plus 1. So what we have in position of f of x is going to be log of x plus 1. So when I am differentiating, f dash of x is 1 divided by x plus 1, and my f double dash of x makes it as minus 1 divided by x plus 1 the whole square, which is less than 0. When it is less than 0, we don't have a convex function, but it is a concave function. We always know that log x is going to be a concave function. Log x is going to be a concave function. So our usual Jensen's inequality will not work, but it will get flipped for. So expected value of f of x will be actually greater than or equal to for my Jensen's inequality. But what will happen in this case? This will become less than or equal to f of e of x. So my expected value of log of x plus 1 will be less than or equal to log of e of x plus 1. Now we may ask the question, wherever I have x, I'll have to replace it with e of x. Will it be the same as e of x plus 1 or e of x plus 1? Will this also be the same? Yes, this will also be the same because we know that e of x plus 1 can be expressed as e of x plus e of 1, which is nothing but e of x, and we know the expected value of a constant is the same. So this and this are both one and the same, and hence expected value of log of x plus 1 is less than or equal to log of e of x plus 1. The same property will hold for log also, that is expected value of log x will be less than or equal to log of e of x. So with this, we come to an end of the problems of your Jensen's inequality. Hope the situation where you will have to apply Jensen's inequality, namely convex function, which means your double derivative has to be greater than or equal to 0, is the criteria. And based upon it, I have or leave the last question for you, e of x. Exponential function is always an positive function. How many times you differentiate, e of x will remain to be the same e of x. So it is always positive and hence always convex in nature, and Jensen's can be applied for it. So having all the ideas left behind for you, I leave this problem for you to solve. For happy learning, keep learning. Thank you.